welcome back to MonkeyByte.
Today, we are looking at a computer most people have heard about, almost nobody has used, and every serious security team has already started preparing for.
A quantum computer.
Not the glowing magic box from a science fiction trailer.
The real one is colder, quieter, stranger, and much harder to explain.
It lives inside metal cylinders, vacuum lines, cryogenic systems, lasers, microwave pulses, and error correction codes.
I'm Sky.
And I'm Blue.
The strange part is not that quantum computers are powerful.
The strange part is that society may have to prepare for them before ordinary people ever see one work.
Banks are watching.
Scientists are watching.
Governments are watching.
Messaging apps are already changing their locks.
Because the machine that still feels unreal is already changing what real institutions do. The first scene is not a desk with a keyboard.
It is a lab where the computer looks more like a chandelier made for a spaceship.
A dilution refrigerator hangs from the ceiling, layers of polished metal descending into colder and colder darkness.
Inside, a quantum processor is being protected from almost everything the world normally does.
Heat.
Vibration.
Stray signals.
The casual violence of ordinary reality.
That is the first thing people miss. Quantum computers are not just faster laptops.
They are machines built around fragility.
A normal computer stores information as bits, little yes or no states.
A quantum computer uses qubits, which can behave in ways that do not fit everyday intuition.
And before anyone gets carried away, no, it is not doing every possible answer in parallel like a cartoon.
Good. Because that line should be banned from every quantum explanation.
It is using quantum states carefully enough that some mathematical patterns become easier to expose.
And care is the key word.
Because qubits are noisy.
They lose information.
They drift.
They decohere.
They behave like a whisper trying to survive inside a thunderstorm.
That is why error correction matters so much.
In 2024, Google introduced Willow, and the important claim was not just that the chip was fast on a benchmark.
The deeper claim was that error-corrected qubits improved as the code got larger.
That sounds small, but in quantum computing it is a door opening.
Because for decades, the problem was simple and brutal. Add more qubits, and you often add more ways for the system to fail.
Willow's Nature paper reported below threshold surface code memories, where increasing code distance suppressed logical error rates.
In normal language, they showed a path where making the protection bigger can actually make the quantum memory better.
Not a finished universal quantum computer.
Not a machine that breaks the internet tomorrow.
But a serious engineering signal.
And that is the tension.
Quantum computing is still fragile enough to be doubted.
But it is no longer vague enough to be ignored.
I think that is what makes this moment strange.
You mean the machine is not ready, but the consequences are already arriving.
Exactly.
I would push back slightly. The consequences are arriving because companies and governments are choosing to treat roadmaps like warning signs.
Fair. But that is how infrastructure changes.
Not when the public understands it.
When institutions stop laughing at it.
The second scene is not a quantum lab.
It is a chemistry lab.
A researcher is staring at a molecular model rotating on a screen, not because it looks beautiful, but because it refuses to become simple.
Atoms interact, electrons shift, bonds stretch, energy states multiply.
And very quickly, the natural world becomes too complicated for easy classical simulation.
This is why the old idea behind quantum computing still matters.
Richard Feynman argued in the early 1980s that if you want to simulate quantum physics, maybe you need a machine that is quantum too.
That idea is not marketing.
It is the reason chemistry and materials science keep appearing in serious quantum conversations.
Because nature is already quantum before humans try to compute it.
A battery material.
A catalyst.
A protein interaction.
A molecule that might become a medicine.
These are not spreadsheet problems.
They are physical systems with quantum behavior inside them.
And that is where the promise becomes more grounded.
Not quantum computers replacing all computers,
Not quantum laptops in every backpack.
but specialized machines helping scientists ask questions that classical machines struggle to represent directly.
IBM has called this the road toward quantum utility, finding cases where quantum systems can produce useful scientific outputs before fault tolerance arrives.
In 2023, IBM and collaborators published Nature results using a noisy 127 qubit processor to study a quantum system at a scale beyond brute force classical calculation.
Important phrase: evidence for utility,
Not final
not proof that every chemistry problem changes tomorrow.
evidence.
And evidence is exactly what this field needs, because the hype has always been loud.
There are roadmaps now that sound bold. IBM has described a path toward a large-scale, fault-tolerant system called Starling by 2029.
That is a target, not a prophecy.
But even a target can change behavior.
Universities train students differently.
Pharmaceutical groups watch the hardware more closely.
Materials scientists start asking which problems might be quantum native.
And investors begin treating a refrigerator full of qubits like a future industrial tool.
This is where I get cautious.
Because most quantum promises are still future tense.
Exactly. The useful machine is not the same as the promised machine.
But the direction matters.
Yes. If the first real applications appear in chemistry, materials, and simulation, then quantum computing enters the world through science before it enters the world through consumers.
Not as an app.
As a laboratory instrument,
Not something you hold.
something that changes what scientists can attempt.
And that may be more important than the consumer version.
Because ordinary people do not need to see the machine for its discoveries to reach them.
A better battery.
A stronger material.
A more precise chemical model.
A drug candidate that would have taken longer to understand.
The public may never touch the quantum computer.
They may only live inside the world it helped design.
The third scene is not a lab at all.
It is a security room.
A bank, a government agency, a hospital network, a messaging platform,
Not panicking.
inventorying,
That word sounds boring until you realize what they are counting.
encryption systems,
Certificates,
keys,
protocols.
every lock that quietly protects modern digital life.
This is the part of quantum computing that already touches ordinary people.
Not because a quantum computer has broken your bank account,
But because the possibility is serious enough that standards bodies and platforms are moving now.
Peter Shaw showed in the 1990s that a sufficiently powerful quantum computer could factor large numbers and solve discrete logarithms efficiently.
Those are not just math puzzles.
They sit under major public key cryptography systems.
So the danger is not that today's quantum computer breaks everything.
The danger is time.
Sensitive data can be collected today and decrypted later if future machines become strong enough.
Harvest now, decrypt later.
That phrase is ugly because it is practical.
In 2024, NIST finalized its first 3 post-quantum encryption standards.
ML-KEM for key establishment,
ML-DSA for digital signature.
and SLH-DSA is a stateless hash-based signature standard.
That is not science fiction anymore.
That is paperwork turning into infrastructure.
Messaging apps move too.
Signal introduced PQXDH to begin protecting conversations against future quantum threats.
Apple introduced PQ3 for iMessage, explicitly framing it around future quantum computers and Harvest now decrypt later risk.
That is the real-world case people should pay attention to.
Not because your phone suddenly became quantum,
Because your phone is preparing for a computer you may never see.
and that is the final human consequence.
Quantum computing may arrive first as a migration burden.
A bank has to update old systems.
A hospital has to protect long-lived medical records.
A government has to protect secrets that must remain secret for decades.
A company has to ask where every certificate lives.
A user simply updates their phone and never notices the cryptographic war happening underneath.
This is why I do not like the phrase quantum apocalypse.
Too dramatic?
Too lazy.
Because the real story is slower.
And more expensive.
A long migration before the machine fully arrives.
A security rebuild in advance of a future threat.
A race between error correction and cryptographic replacement.
That is much scarier than a countdown clock.
Because it means the future is already changing the present. The strange part is not that quantum computers are hard to understand.
They are.
The strange part is that the world is already making room for them.
Scientists are asking which discoveries become possible.
Engineers are trying to make fragile qubits reliable.
Security teams are replacing locks before the thief has arrived.
And ordinary people may experience the shift without ever seeing the machine itself.
A better material.
A stronger encryption standard.
A new scientific instrument hidden inside a lab most people will never enter.
That is the quantum bet.
Not that the machine will become magic,
but that it will become useful enough to rearrange what humans prepare for.
This was MonkeyByte, built by AI, questioning AI.
Thank you for watching. If this story made you think, like the video, subscribe and join us for the next one.